Did you know that under certain conditions, hot water freezes faster than cold water? And have you ever wondered what's up with that? Because so have scientists, and a new hypothesis may have finally figured out why this happens. The phenomenon I'm talking about is called the Mpemba effect, named after a Tanzanian student named Erasto B. Mpemba. Yep, it's another story with ties to Tanzania.
How funny.
What are the odds? Small world. Anyway, in the late 1960s, Mpemba ran some experiments and found that under certain conditions, hot water freezes faster than cold water. But scientists still don't exactly agree on those conditions. And the fact that the effect doesn't happen all the time makes it kind of hard to study. That's probably part of the reason why scientists don't all agree on why it happens either. For a long time, the most popular idea was that hot water evaporates more quickly, so it loses more mass and it needs to lose less heat to freeze. But the Mpemba effect happens in closed containers with no evaporation. So a different explanation showed up in 2013 when there were reports that a team of researchers from Singapore had found the answer. They said the bonds between molecules in boiling water are more flexible and ready to give up energy in the form of heat than the molecules in cool water. Scientists didn't love this explanation either because it still didn't explain why the effect only happens sometimes. Well, in January, researchers came up with a new hypothesis, and it relies on the idea that the bonds between H2O molecules structurally change in response to temperature. Basically, the molecules in hot water are constantly moving, so there's a lot of disorder in the system, aka entropy. Cold water molecules usually cluster together and make weak bonds. As the water heats up, those bonds break. So in the same way you'll get colder on your own than when you're huddled up with a group of friends, these buzzing hot water molecules may be able to form ice crystals in a freezer faster than the clusters of cold water molecules, since the cold water molecules have a tighter arrangement that takes time for the temperature to change. And here's an important caveat. This effect wouldn't necessarily appear if there were a lot of salts and minerals dissolved in the water, since the water wouldn't form as many clusters at cold temperatures. This explanation neatly addresses both the phenomenon itself and the difficulty of repeating it under laboratory conditions. But that doesn't necessarily mean it's true either. File this under maybe, but we will get back to you when we know for sure.